Hi, I'm Andy Rudoff, and I'm the lead persistent memory software architect in the Optane group at Intel. And material for today's presentation was also contributed by my coworkers and engineers, Principal Chet Douglas and Tiffany Kazanicki. And today I'm going to talk about the changes that we made to support persistent memory in the Compute Express Link specification, or CXL. And if some of those terms are not familiar, don't worry, I'm going to find what they are in just a moment. Actually, there's quite a bit of detail that I could talk about here for hours. I mean, it took us months to do this work. In less than half an hour, what I'm going to do instead is provide a kind of whirlwind tour that shows you what these different components are, how they fit together, and where I see them going in the future. If you're actually watching this on April 22nd during the summit, I just want to remind you that you can ask questions using the chat window. Okay, so first let's talk about how persistent memory today is connected up to the system. All the persistent memory products in the marketplace today connect to the memory bus. And so here I've drawn a little cartoon of how Intel's Optane persistent memory connects to a system. You can see on the left side of the slide, I'm showing the computer cores, the cache hierarchy, memory controller. But at the bottom, there are slots where we plug in the DRAM into the DDR slots, and also persistent memory into some of those same slots. And the green path here, marked app direct, is the persistent memory programming model. It's the direct access path. And on the right, I've put a little snippet of the programming model to remind you that this is what gives applications direct access to persistent memory. Once the OS sets it up, an application can do a load directly from persistent media. And for the Optane media, it can get that value in a few hundred nanoseconds, something that's not really possible for any storage devices because of the lack of direct access. Also on the left side of the slide, notice this red path, which I've marked memory mode path. This is kind of unique to the Optane media because it's very high capacity and its price point makes it cheaper than DRAM. And so oftentimes people want to use it as a volatile tier of memory, even though the media happens to be persistent. And I'm pointing this out because the desire to use this both as a volatile and persistence did influence our direction when we decided how to add this to the Compute Express Link specification. So we've been talking about the programming model for years now. When we all started working on persistent memory, a bunch of companies got together. We formed this technical work group in SNIA, where we created the persistent memory programming model. There's a diagram here that I've been showing for years. There's lots of information you can find out about it. What we don't really talk about as much is how does the operating system know there's persistent memory installed in the system? And how does the driver do things to the persistent memory other than just loads and stores? Like it wants to do management operations, like reconfiguring it or checking its health. So that is answered by looking at what we've added to the ACPI framework. And again, this was done years ago when we first started working on this model. We added this table called the NVDIMM firmware interface table. We added it to ACPI 6.0, or NFIT for short. It's the existence of this NFIT table that causes the driver to load its driver stack for NVDIMMs. And so this is how you communicate between the reboot environment and the OS about the existence of the memory. Now, when the driver wants to do something management-wise to that memory, it does that by calling out to these device-specific methods, or in ACPI terminology, it's often written as _DSM. These things know how to do things like update firmware or check health or so on. And they understand how to do the vendor-specific interfaces to make these things happen. That abstracts away those vendor-specific details and allows these drivers in the operating system to be generic. So all of this stuff that I'm showing at the bottom of the slide, I basically think of it as just part of the BIOS. The BIOS is the thing that creates the NFIT. BIOS is where these DSMs live. And that allows the complexity to be kind of put down in the BIOS, whether that's good or bad, you'll see in a minute. It allows this generic driver to be in the OS. So we've been doing this now for years. This has been the way things work for quite a number of years now, and we've learned quite a bit from it. On the pro side, I think it was a really great idea that we took these things that all these different vendors were doing that were different. They were all vendor private interfaces, and we unified them with the ACPI infit table and the DSM. So that helped us get generic drivers upstream into the operating systems pretty early, and that was a big pro. The DSMs abstracted away the differences and allowed these drivers to be generic, and that was a pro. In fact, I'd say this mechanism has evolved fairly gracefully. We've added a few things to it over the years, but we really haven't had to go back and correct any horrible errors in that definition. On the con side, as we look forward to scaling this more, ACPI isn't really built for that. It's not, it only has very rudimentary support for hot plug. It's not meant for kind of an unknown number of sockets like you would get with CXL, where there are switches, perhaps multiple levels of switches, and hot plug sockets at different levels. That's not a great fit for ACPI, so that's a bit of a con. And I have to say the DSMs, the complexity has been a little difficult to maintain because they're down in the BIOS, they're hard to debug. When we do find bugs, the fixes mean that you have to release new versions of the BIOS. The BIOS is delivered by, individual OEMs, so that's quite a bit of logistical challenge there. In fact, it's virtually impossible to create a BIOS that supports multiple persistent memory products because the OEM would have to glom together all these vendor private DSMs from different vendors. So currently nobody even tries to do that. It's just difficult to get to work. So now let's talk about Compute Express Link. There's a lot of information out there about this new class of interconnect. So I'll just give you again, the whirlwind explanation of what it is. On computeexpresslink.org, there's quite a bit of information, a lot of training materials. I snagged one of these slides from the training materials. CXL is an open industry standard for a high bandwidth, low latency interconnect. If you kind of look down on this slide a little bit, see one of the key points. It's based off of PCIe physical signals. So the PCIe electricals have these new CXL protocols tunneled over them, CXL.io, CXL.cache, and CXL.memory. And I'm going to focus on the CXL.io and CXL.memory protocols, and you'll see why in a minute. Just to give you a little history about the specification, CXL 1.1, which was really the first fully usable version of the spec, was published in June of 2019. The February after that, my coworkers and I went to the CXL committee and started working on adding the persistent memory support into 2.0. 2.0 spec was published last November. It's backward compatible with 1.1, and that's where we added the persistent memory support. So let's talk about the types of devices that you have in CXL. Here are 3 representative usages of CXL. These are typically referred to as a type 1, type 2, or type 3 device. And you'll notice the type 1 and type 2 devices, these are both accelerators of some sort. And so that's not what I'm here to talk about today. I'm going to focus instead on a type 3 device. This is a device that allows you to expand the memory of the system. It allows you to plug memory into your CXL slots and access it just like you had plugged that memory into DIMM slots. It's load store accessible by the CPU and by software. So that seems like kind of a natural place for us to put persistent memory when CXL arrives. So let's talk about what we added to the CXL specification to support persistent memory. Here it is in kind of high-level bullets first. As we were looking at the changes to make to the CXL spec, we realized that most of what we were going to propose makes sense for all memory types. So we should really focus on that. Everything that we added with an eye towards making it work for volatile memory and persistent memory. And we only put persistent memory specific things in when absolutely necessary, when it really only applied to persistent memory. So how do you find the persistent memory devices? Remember, for NVDIMMs, it was this infit table. But since CXL is built on top of PCIe, we wanted to use the PCIe enumeration that's been commonly used for PCIe devices for a lot of years. this really leverages the PCIe frameworks that are mature and part of every OS, including the ability to hot plug. And remember, the N in the NFIT table, the N stands for NVDIMM. So that table really is just used for NVDIMMs, things that plug into the DIMM slots. If it plugs into CXL, the PCI enumeration is what gets used. Then we added some memory mapped IO registers, some things for exposing some status and some bookkeeping, but mostly the most important thing we added was a mailbox interface. And the mailbox interface allows us to implement a nice flexible command interface where we can add commands. Now, for the NVDIMMs and the Optane product, all these commands that are shipping today are vendor private. They're specified in some spec that's not public, and the BIOS knows how to speak them in the vendor specific code that's in the BIOS. Now we're adding all these changes to a public spec, and we really want to make the entire command interface standardized so that anybody can read the standard and interact directly with these devices. So that was definitely our goal here. But what you end up with is a spec that's just a kind of terse list of commands. It's not quite clear how they all fit together. So we provided an ancillary document, which we call the driver writer's guide, that helps show you how all the pieces fit together. And I'm going to talk more about that in a minute. That's delivered as a separate document from the CXL spec itself. And then finally, there were some minor changes that we made to other specs like ACPI and UEFI. The bulk of our changes went into the CXL 2.0 spec. Okay, so let's talk about some of those mailbox commands. Now, remember, all those commands, all the ways for you to communicate with these system memory products that are shipping today, they're all vendor private. And we're changing it. We're making them into a standard. And standards are a double-edged sword. For one thing, now that they're all published and everybody can read about them, you get these nice generic drivers. You don't have to have a vendor-specific driver for each one of these products. You can use a generic driver because it speaks a standard protocol, kind of like how there's a generic SCSI driver and a generic NVM Express driver. On the other hand, every time you want to add something or change something, you get to go visit the committee. And the committee will scrutinize what you're adding, and they'll try and make a different way of implementing it that's more clean or more clear, and the process can take a long time. But in the end, it's all worth it because you end up with a better command. You end up with something that has community buy-in and it makes more sense. So it really is worth the extra work, I believe. We learned a lot from what we did with NVDIMMs, and a lot of the same people that worked on the NVDIMM committees are part of the CXL committee. So we really got to leverage a lot of that knowledge and a lot of that work. And a lot of the same people had to live through some of the pain points of our first attempt with NVDIMMs. And so we also got to fix those as we went along. Now, as we started adding these mailbox commands to the spec, we quickly realized that many of these commands apply to any CXL devices, not just memory devices. And so you'll see on the right, the first table that we added to the CXL spec is not just for memory devices, it's for any CXL device. And so we added this to chapter 8. All the details, you can read about them in chapter 8 if you're interested. I'm mostly just giving you a flavor for what the commands look like. You can see it's things like fetch event records, or upgrade the firmware of a device, or get the logs. All of these things are not really specific to a memory device. They make sense for any CXL device. So that's the first table of commands that we added. But after that, we did go ahead and add a table of memory device commands. And this is much bigger. It's so big, it doesn't even fit on the slide. You can see the full table in the spec. But again, I'll remind you, now all of these DSMs are gone. So the OS uses these mailbox commands directly. The OS driver writer reads this spec and just does what's in the spec directly. And that means a lot of the complexity from the BIOS has been removed. We removed thousands of lines of code from the BIOS, and that was really great because that really was a pain point maintaining that. On the other hand, we added complexity into the OS, so it's a trade-off. It does allow us now to have generic persistent memory support in the BIOS, in fact, generic support for any kind of CXL memory device, and generic OS drivers in the operating systems. On the right, you can see how some of these commands are marked with an M for mandatory. That means for a CXL memory device, these commands are required. Every device should have an identify memory device command, for example, you can see on top here. And then some of them are marked with PM. That means they're mandatory only if that device provides persistent memory. So only if a device has persistent memory on it, you need to provide the get LSA, the label storage area command. I'm going to explain what that is in a moment. So that gives you an idea of how these commands are organized. Many of them are optional, many of them are persistent memory mandatory, and then many of them are mandatory for all memory devices. So here's an example, that very first command I told you about. If I look at the identify memory device command in our spec, I'll see the output payload is defined like this. It returns back the total capacity of the device. How much memory is that device providing? How much of that capacity can only be used as volatile memory? How much of that capacity can only be used as persistent memory? And if the device can actually be changed between volatile and capacity, there's this idea of partitioning it one way or the other. So you can see, without going into too much detail here, we tried to just make this a very flexible interface. You can imagine somebody building CXL attached DRAM devices, or CXL attached persistent memory devices, or things like the Optane device that I mentioned before, where you can have some of it partitioned for volatile and some of it for persistence. This is powerful enough of an interface to handle all of those use cases, and that was really our goal here. Again, the device driver writer's guide really helps pull all this together. The CXL spec is kind of terse legalese, language. Chet Douglas draws these beautiful flows, and I know this is a lot more detail than you can read on this slide right now, but you can go to the guide and actually read it in more detail if you're interested. I'm just trying to give you a flavor of what these flows look like. This is the boot flow. Chet shows you how all the different parts of the systems work together and the timeline of booting and what happens. And in particular, we're the Intel guys, so we had to decide what's the division of labor between the Intel BIOS and the OS. And so these Intel specific details really needed to be documented. They don't really belong in the CXL spec because CXL is a vendor neutral specification. It's not Intel specific. So that's why we wrote this driver writer's guide to document our flows and our algorithms to explain how all this is meant to be used. And the driver writers, use this guide heavily as they're developing the drivers for CXL. It's published on intel.com, so you can read it. It's free and open to anyone to read. So let's talk a little bit about some of the hard stuff that we had to do, some of the more interesting problems we had to solve. The first one I would say is interleaving. So as you might know, when you plug DIMMs into the DIMM slots of a system for performance, the system typically interleaves across memory DIMMs. Well, the same thing is true when you plug memory into CXL. You want to be able to interleave across them for performance. That's done with these things called HDM decoders. HDM stands for Host Managed Device Memory, and it's a CXL term for these decoders that are described in the standard so that an OS can program them to interleave across devices. Now, this is a new idea to PCIe. I said before, PCIe has this mature stack, it's been around forever, that's true. But collecting PCIe devices together into interleave sets, that's a new idea. So that's something that OS vendors have to implement. And it's an important concept for persistent memory in particular. For volatile memory, if I change the way I interleave every time I boot, the performance characteristics might be slightly different just because of the way I'm interleaving. There's no correctness issue. But for persistent memory, if I change the way I interleave after the second time I'm booting, if it doesn't match the way I booted the first time, you've lost your data because the layout is now different. So it's really critical that the interleave be set up exactly the same way every time you boot for persistent memory. So in order to allow this, we've invented this idea called the label storage area. It's defined in the CXL 2.0 spec. There's quite a bit of detail on it in chapter 9. And it provides these region labels. Region is another word for interleave set, so that they can be set up the same way every time you boot, as well as namespace labels, which are ways of just carving up the capacity, very analogous to the namespaces in NVM Express. Just to show you what some of these labels might look like, here's a little cartoon of a CXL host bridge. It's got two-way interleaving between two root ports, and these host physical addresses come in the top and get routed by those HDM decoders. I'm showing a couple of switches here plugged into these root ports and 4 devices in each switch. So you can see here how if I'm just looking at increasing physical addresses, the 1K of information kind of gets interleaved across these 8 devices numerically here. At the bottom of the slide, I'm showing you what the label storage areas would hold. And so for each device, the label storage area describes that device's contribution to the interleave set. How many devices are in the interleave set? What's this device's position in the interleave set? What's the interleave granularity for this device? And that allows the operating system to reassemble these interleave sets correctly and in the right order, or even figure out if there are missing components or if there's a misconfiguration. So you can see why these labels are so important for interleaving. A second kind of a difficult area to deal with is hot plug. So PCIe is a hot plug bus, and CXL therefore is a hot plug bus. So we wanted to be able to keep the BIOS simple again and have the hot plug handled just by the operating system. To do that, remember the HDM decoders are part of the CXL standard, so the OS knows everything it needs to know to interleave within CXL. But how do you interleave across host bridges? To do that, the BIOS pre-configures platform-specific interleaving and provides these windows, like these blue boxes here represent little interleave windows that are set up ahead of time for volatile memory. The green ones are little windows for persistent memory, and this little colored window is a window that goes across all these host bridges of interleaving. Now the OS has everything it needs to know. If you just walk up and plug in a CXL memory device, the OS can set up interleaving in these windows without any BIOS involvement. That turned out to simplify things quite a bit. We like it so much that we just have the BIOS completely ignore persistent memory now. And it boots up and the OS just goes ahead and uses the same flow to configure the interleaving for all the persistent memory in the system. With the one exception being if you need to boot from persistent memory, then the UEFI driver will set up just that boot device. So that was a pretty interesting and rich area for us to deal with. Another is what happens when you have power loss. Now, you may be familiar with NVDIMMs. There are features called ADR and EADR that flush things to the NVDIMMs on power loss. On CXL, the analogous mechanism is called global persistent flush. And it's very simple when it works. Everybody's happy and all these stores get flushed on power loss. It's more complex when it fails. There's a lot to consider. There's something called the dirty shutdown count that explains to software that something failed. Fortunately, it was already part of our programming model. Any code that was written to that programming model and works for NVDIMMs will also work for the CXL devices, even with this flush on fail mechanism. You can see Chet's diagram for this on the right is really complex. There's a lot of details there. I can't go into it today, but see the guide for details. There's actually a lot of really interesting things about this. Okay, now let's talk about the software enabling. The good news is the momentum around CXL is really huge. For NVDIMMs, it was just a few of us in the room working on the changes to ACPI. For CXL, it's dozens of highly engaged companies, including all the major operating system vendors, OEMs, ISVs, IHVs. It's really been a joy to work with. And there's so much momentum about it that even now, well before there are CXL devices, a preliminary generic memory driver has already gone upstream in Linux. This was orchestrated by Dan Williams, who is the maintainer of the NVDIMM framework. He's made sure that the architecture reuses as much of the implementation as possible from NVDIMM, and he's really done a great job there. A lot of this was made possible by adding support to QEMU, which is the virtualization environment on Linux, to emulate one of these Type 3 CXL devices. Patches to do this were created and posted publicly by Ben Wadowski and our Linux team, and that allowed us to do this very early development of the driver and really kind of get ahead of the curve on the implementation. But in general, I have to say the cross-company, cross-committee collaboration on these specs has really been a joy to watch. I think it's going to prevent lots of messy collisions from different implementation decisions in the future. The best part, of course, like I mentioned, is that there's just generic BIOS support now for persistent memory, and generic OS drivers are emerging. On the challenge side, you might have thought we were all done. We had the NVDIMM framework and the NFIT table was out there. If you had a kernel that supported that, as new products came out, your kernel didn't need to change.
but now you will need a kernel that understands CXL. And that either means a new driver or maybe even a new kernel. It's not quite clear if we can backport drivers because of the new, more complicated things driver has to do, like deal with interleave sets. Tooling also is changing. There's on Linux, for example, there's an NVDIMM tool called NDCTL that is now evolving into the CXL version of that same tool. So in summary, of course, the programming model remains the same. If you've written an application for persistent memory, we're very adamant that you protect the programming model, protect ISVs so that their code doesn't break. It continues to work, and in fact, an application doesn't really have any idea whether the persistent memory is plugged into a DRAM slot or plugged into CXL. CXL offers us quite a bit of flexibility for expansion. You can now add all types of memory, including persistent memory, not just in the memory bus, but in these CXL slots, and have it be addressed as memory. It's quite a bit more scalable that way because you always have a fixed number of DRAM slots, but CXL is a much more expandable bus and a much more flexible bus. We added our changes to the CXL spec as of the 2.0 specification, which was published last November, and we're seeing the OS enabling emerging. So I know this was a whirlwind tour. I hope you enjoyed it. I hope you got something out of it. The slides are available to you on this website. Thanks very much, and hope you enjoyed the talk.